Thank you so much, Matthew. Thank you all for attending this seminar. So I will just keep my camera off that it doesn't take bandwidth much. So can you see my screen properly?
Yes.
Thank you. So I will talk about the impact of ocean model resolution on South American air sea interaction during the extreme rainfall event. Here are my collaborators. So this is our ongoing work. So I will happy to get your feedback to improve the work. So South American monsoon, also called as SAM, it is like mainly the austral summer. More than 50% of annual precipitation are means received by this area of the South America, and this area is strongly agricultural based and also densely populated area. So, and this short time precipitation actually are hugely influence the economy of this area. So, but the SAM actually exhibit like a spatiotemporal variability ranging from diurnal to decadal. But so here I mainly will focus on the interseasonal variability. So first I little bit give an introduction about the characteristics during the austral summer, where the actually land ocean contrast bring the precipitation over the ocean. So in the upper level of December, January, February, a anticyclone over this area is visible. Whereas in a lower level, there is a two high pressure system in the subtropical, one in the subtropical Atlantic and one in the Pacific, where there is a level, low uh, pressure system in the central American region, South American region. There is a ITCZ, and there is a low level east, northwesterly. So this called as a low level jet, and this actually influence this South American convergence zone, which is the mainly bring most of the precipitation over this region. So there are two actually the interseasonal time scale two zone are mainly get strong precipitation. So this over the southeast Brazil, this region is called here I will call it as a Sabra, and the one in the south eastern America, this I will call as a Sesa. So these are dipole-like pattern, and so these are though. So when the Sabra is getting more rainfall, Sasa has a less precipitation, and vice versa during the opposite phase. So actually, it is known that Madden-Julian oscillation can trigger these events. So it induces a Rossby wave trail, which changes the circulation over this region and bring the precipitation. So when there is a this kind of geopotential height pattern, it actually influences the low level jet. So you can see that there is a weakening of our northward shift of the low level jet, and it bring precipitation over the Sabra region. Whereas when the low level jet intensify and shift toward the south, the southern region, the Sasa region get the maximum precipitation. So this is well known that MJO or the teleconnection pattern create this kind of precipitation event, but now recent studies are showing that the local hearsay feedback also have a strong influence on these events, but this is like less explored, and so our study mainly will focus on the role of local ERC feedback on extreme precipitation event in Sabra and Sasa during the austral summer. And for that, we will use two retrospective hindcasts with a different ocean model resolution to see how the ocean is influencing these patterns. So here we use two global retrospective forecast using CCSM4, and two configuration are used. One is low resolution, which is our ocean model is 1 degree resolution, and so here the ADs are parameterized, where the second one is high resolution, which is 1/10 degree of the ocean model resolution. And so this high resolution model actually resolve the ADs. So we use the forecast from 1982 to 2015, where each January of the year is initialized with the CFSR initial condition and run for the entire year. And so here we actually use from January to March, as our model is initialized in January. So in the initial period, we'll get more better better simulation. So, and the other data set use a Reynolds SST, Persian and precipitation, GPCP precipitation, and ERA reanalysis data. So as we are focusing on the intra-seasonal time scale, so we are actually try to get the time, the cycle of 90 days period, like below and like to the 90 days, which is more kind of MJO time scale. So here we did use the filtration. So we actually remove a 5-year running mean to remove the all inter annual variabilities like the ENSO and all, and also we remove 120-day running mean to remove the interseasonal variability. And so we used the precipitation time series for our composite analysis. So we used the Sabra, which is 20 south to 18 south, and for 47 west to 40 west, and Sasa, which is 35 south to 30 south and 60 west to 53 west. And we prepare this time series, and then we make a composite of the event, which is actually crossing the 90 percentile. So here I showed a comparison of the precipitation anomaly of the GPCPA high resolution and low resolution model for both Sabra 90 and Sasa 90. That means the precipitation for these events are more than 90 percentile. So you can see the observed pattern over the Sabra has a two bulb of precipitation. So there is a one maximum over the land and one maximum over the ocean, and there is a less precipitation in the coastal area because of the Brazil current. So there is a cooling because of upwelling, and which actually decreases the precipitation over this region. And this feature is prominent in high resolution. So high resolution has a significantly two bulb of the precipitation maximum, but the low resolution has a lesser signature over the ocean mainly. And so Also the Sasa region, also the precipitation has both over the ocean and the land. So now how the model is capturing these events. So to show that, here I showed the difference between high resolution and observation in the left panel, low resolution and observation in the middle panel, and difference between high resolution and low resolution. So both the model are underestimating the precipitation, but the high resolution is actually is better in predicting the means capturing the precipitation mainly over the ocean for both Sasa and Sabra region. So now here I showed the evolution of this event. So I prepare a lead lag composite where zero lag is actually the event where the precipitation is like more than 90 percentile, and then I prepare the composite from lag -4 to lag +4. So the left hand is the GPCP, and then I showed the high resolution, and uh, rightmost panel is the low resolution. And here the showed the same, but the difference of the two model with respect to observation, and this right panel is also the high resolution minus the low resolution. So you can see here that the with these all lag, high resolution is doing better in the both the ocean and the part of the coastal region to capture this precipitation event. So now here I showed the time evolution of a particular box of zebra and sesa. So this is mainly over the land. So you can see the black line is observation, red line is high resolution hindcast, and blue line is low resolution hindcast. So it is very means prominent that the ensemble mean the high resolution is showing a better than the low resolution. So I don't maybe I forgot to mention. So these are figures are actually for the model we use a three ensemble, and we did an average of these three ensemble to show the model ensemble mean composite. So these are the composite from the ensemble mean. Now I try to see the how the this precipitation event is linked to the SST. Does SST has a signal when this pattern is emerging? So here I showed like from 1983 to 2015. I take 11 January to 31st March. So we remove that first 10 days of the SST data set, as that has a signal of data assimilation, and so the major pattern is arriving as changes due to the data assimilation. So that's why we took from 11 Jan to 31st March, and this is showing the observation has a warming which is like 20 days before the precipitation peak, and then during the precipitation peak there is a cooling, and which actually sustain for some more time, like next 20 days. And though the this SST pattern is weaker in the models, but high resolution actually capturing this initial warming and then cooling in the coastal region of the South America pretty good. But the low resolution model does not show this pattern, and the cooling also is very less over the coastal area when there is a maximum warming, so which suggests the feedback between the cloud and SST is weaker in the low resolution, where the high resolution is actually capturing it much better. Now, to see the how the uh, geopotential height, which is a signal from the teleconnection from the Pacific, and the wind is actually in this two model in comparison of the uh, uh, observation. So observation here, it is Reynolds, SST, and the atmospheric component are from the ERA dataset, whereas high resolution and low resolution is capturing this geopotential height pattern good. So the in both the model, this teleconnection pattern is pretty good. But when it is coming in the local feedback, that SST signal is much more in the high resolution, and you can see that the wind pattern, this wind pattern, which is actually bringing the strong precipitation and suggesting a cyclonic circulation, is much stronger in high resolution than the low resolution. So this also the reason maybe that a better wind is actually driving the stronger moisture flux, and are the reason for the strong precipitation anomaly in the high resolution. Now we try to see what are the component actually attributing this warming, initial warming, and mainly the cooling during the uh, Sabra event. So you can see that this figure is showing the turbulent heat flux, and which is actually positive when the ocean is receiving heat. So when you are seeing the negative value, that means ocean is losing heat due to the turbulence fluxes. And so here for high resolution data, the turbulent fluxes negative value is much higher, and this is a reason that ocean is actually losing heat, and which is our reason for one of the reason for SST cooling. And low resolution is underestimating it with and though there is a turbulent flux, but the magnitude is weaker. Now, how is the ocean mix layer? Because the flux is actually going to the ocean mix layer, and then it is giving SST signature. So here I again show the mix layer anomaly from -20 to +20. So the same time I showed the SST pattern. So you can see here that there is a shallow mix layer initially when we got some warming signal, and then during the event the mix layer is high. So the actually, so there is two process. One is a ocean, the fluxes are showing that turbulent fluxes are less, so ocean is reducing that. Again, the deeper mix layer, so the flux is going to the ocean is have to make warm the deeper mix layer. So both are acting towards support the cooling during the Sabra event. And these mixed layer signal are very very weak in the low resolution data, so you cannot see particular pattern. And because the ocean eddies are not resolved in this low resolution model, it didn't capture this kind of mixed layer anomaly. Now, as we use the ensemble mean, we found that there is a strong spread between all the ensemble for both in high and low resolution model. So when we did the ensemble mean, the subseasonal variability might be cancelled out because the spread, and maybe the reason for this lower magnitude of rainfall over this Sabra region. So we took another approach to see is it that if we take an individual ensemble, how the precipitation anomaly are. So here what we did, we took the each ensemble separately, make the time series separately, and prepare the composite for these three ensemble for high resolution and low resolution. So this figure is showing that three ensemble of the high resolution composite with a separately taking the each ensemble, and in the right we showed the low resolution. So you can see that still there is a better representation here in the high resolution, though the magnitude improved largely. So, but the this dipole of two precipitation over one over the land, one over the ocean is prominent in the high resolution, and the low precipitation in the coastal region. So now we actually did make a composite from this separate composite. We did a ensemble mean, so we prepare the composite separately and then average for these three ensemble. And here is the high resolution and low resolution. As I told that the magnitude is increased significantly, but we found that the still the high resolution and low resolution model has a difference. So here you can see that the low resolution is showing like a more precipitation in the lag -2, means it's suggesting the precipitation is event is starting earlier in the low resolution. So but during the peak event the high resolution is doing better in the ocean and the land. But here in the coastal region again low resolution is overestimating because of the lack of the upwelling over this Brazil Current region. So this also suggests that the individual ensemble, if we take that, is also better representing the precipitation event in the high resolution model. And how the SST when we are taking this in a like each ensemble. So this is for high resolution minus 22 plus 10, and this is plus 20, and this is for the low resolution. So here in all three ensemble is showing that warming before the event, the magnitude is varying each ensemble. The cooling is very prominent in the both the three ensembles in high resolution, and it persists. But this pattern is absent in the low resolution. Means like cooling is only visible very weak, and so it suggests that the precipitation or cloud SST feedback is very low in the not very good in the low resolution, which may be the reason that the low resolution high resolution with a better SST precipitation feedback showing a more better representation of the these events. So in summary, so both hindcut produce the observed rainfall variability, which suggests that the remote teleconnection are broadly consistent between both the models. So in the with the uh, AD parameterized model, the teleconnection pattern is good, and that is the reason that it is capturing the events. Whereas high resolution hindcars are capturing the realistic the extreme event with the magnitude and temporal evolution both. So it suggests that improved local earth interaction in high resolution hindcars simulate better local earth feedback, and the reason for the better agreement of the precipitation and assisting the observation as observation, and also suggested that the subseasonal and two seasonal prediction may be improved by using a better ocean AD resolving model. So as I told, it is an ongoing work. So in the future we will explore the both heat and atmospheric moist ocean heat and atmospheric moisture budget to conclude the our like or to confirm our claim. And also we will see how the inactive phase or the dry phase are capturing in these two regions, and how the local airship feedback is influencing these dry phases. Yeah, that's all. Thank you so much for listening. If you have any question, I would like to address.